So in the last two videos, we've talked about how to perform long division and how to perform synthetic division. In this video, we're going to start talking about what are some applications of synthetic division beyond just using it for division. So let's consider this problem where f of x is the numerator and g of x is the denominator. So let's divide this using synthetic division. So I'll take the opposite sign, the 0 of the denominator. Let's see if we need any placeholders here. We got to the fourth power, to the third, to the second power, we're going to need a placeholder in here. To the first power and a constant. So we're going to put 2, 7, then the placeholder 0, 1, and negative 12. So now let's perform the synthetic division. So we always drop the 2, multiply, negative 3 times 2 is negative 6. Add those, I get 1. Negative 3 times 1 is negative 3. Add those, I get negative 3. Negative 3 times negative 3 is 9. Add those, I get 10. And negative 3 times 10 is negative 30. Add those, and I get negative 42. So negative 42 is the remainder. So remember some consequences of this is that x plus 3 is not a factor of f of x here because the remainder is negative 42. Now let's try substituting this negative 3 into f of x. So sub it in for x. And if I do that and I multiply this out, it comes out negative 42, which happens to match the remainder here of negative 42. So the question is this a coincidence? Will this work every time? So what we just noticed is that if I do synthetic division with a negative 3 and look at the remainder, that's the same as if I substituted negative 3 in for x and it comes out the same number. So on the next problem below this one, you're going to pause the video, do the synthetic division, then substitute in the x value and see if the remainders come out the same. So after completing the synthetic division, you should notice that the remainder here is the same as after I substituted 2 in for f of x. Now that's going to be true every time we do synthetic division. Now the question we have is, why is that happening? So let's take a deeper look at what's actually happening in here and why that's happening. So if I were to divide 25 by 3, I would say that's 7 with a remainder of 4. In other words, that's the same as saying 25 is 7 times 3 plus the remainder. Well, we can do the same thing when we set up our polynomial like that. Since I got x squared minus 5x plus 3 remainder 9, I can say that that f of x originally is the same as x squared minus 5x plus 3 times x minus 2 plus the remainder. So this is equivalent to f of x here. This whole thing is f of x. It's just in a different form. So if I substitute 2 into here, since I'm substituting 2 into here, that's going to make this equal 0. All of this is going to turn to 0, and I'm only left with the remainder. So that's why this works. So this is the remainder theorem, and what we've just used is something called synthetic substitution. So if I use the 2 and do synthetic division, I can just look at the remainder, and that's the same as if I substituted 2 in for x. So let's get through the theorems that come out of this. So the first one's called the remainder theorem. And that says, if the polynomial f of x is divided by x minus k, then the remainder r is equal to f of k. So let's talk about that in terms of a concrete example. So let's say I divided f of x by, say, x plus 2. So if I divided by x plus 2, and the remainder, let's say, came out 7, then that would mean that if I took f of negative 2, the opposite sign of x plus 2, then it would come out to be 7. And we saw that on the previous examples. And so that process of using the remainder theorem is called synthetic substitution. So if I want to do, say, f of 5 and figure out what that equals, using synthetic substitution, I can just do synthetic division with a 5. Notice there's no sign change here. Only when we flip from the factor is there a sign change. And then I can just look at the remainder to see what that would equal. Now the consequence of this is if x minus k is a factor of f of x, then there's not going to be a remainder. So the consequence is, if, let's say, for example, I was dividing by x minus 1, and the remainder came out to equal 0, well, that would mean both that x minus 1 is a factor of f of x, and that positive 1 is a 0 of f of x. In other words, if I substituted 1 into f of x, the outcome would be 0. So let's think back to the previous example. We divided f of x by x minus 2, and the remainder was 9. So let's go through some of these theorems in terms of what that means. Well, in terms of the remainder theorem with synthetic substitution, that means if I had done f of, and again the opposite sign here, so if I had done f of 2, that since the remainder is 9, I know that f of 2 has to be 9. Now think of all the other consequences of this. Since the remainder was not 0, that means that x minus 2 is not a factor. And since I substituted in 2 and it came out 9, not 0, that means that 2 is not a 0. So you want to get used to that. If x minus 2 is not a factor, then 2 is not a 0. If x plus 5 is not a factor, then negative 5 is not a 0. If x minus 7 is a factor, then positive 7 is a 0, and so on and so forth. So let's try this down here. This one asks us to use synthetic substitution to discover what g of 1 is. Now remember, I could always substitute 1 in for x to figure that out, but we want to specifically use synthetic substitution. So unless I'm working with x plus minus something, I do not change the sign when I use this. You should make a note of that. So when I go to do the synthetic division here, I'm going to use that 1. Let's see if we need any placeholders here. Squared, linear, constant. We do not need a placeholder. 2, negative 7, and 5. So now I'm going to do synthetic division with the 1. Drop the 2, multiply, add, 0. So I just showed that g of 1 would equal 0. And you could always verify that. If I substitute in 1 here and 1 here, I'll get 2 minus 7 plus 5, which is 0. So think about what the conclusions you make here. Well, since I substituted 1 and the outcome was 0, I know is 1 is a 0. And I also know that its factor, x minus 1, is a factor. And of course these are both of g of x. So that's how I can use synthetic substitution to evaluate function notation, and then it'll also be able to tell me if that number is a 0 and if its corresponding factor is actually a factor of the original function or not. So you want to finish this up by trying this example right here. Find h of negative 2 using synthetic substitution, and then what other conclusions can you make after you do synthetic substitution? And you should think back to the conclusions I made on this example.